I'd like to welcome you today, Melanie, to the Citrix Algo Hour. Melanie is a PhD student at Princeton, where she is advised by Charles Pfefferman. Her research focuses on understanding the geometric features of data mathematically and developing machine learning methods that utilize this knowledge. Seems pretty cool. Prior to her PhD, she received undergrad degrees in math and physics from Leipzig, and she also spent time at MIT's Laboratory for Information Decision Systems and the Max Planck Institute for Math in the Sciences and the research labs of Facebook and Google. So I'm really excited to hear you talk today. Welcome.
Yeah, thanks a lot for the introduction and also for the invitation to speak. So my talk today is going to focus on geometric methods for machine learning and optimization. And much of this work is motivated by the fact that in many machine learning applications, we encounter non-Euclidean data. So this can be in the form of relational data. So when we study social networks or when we study languages where we encounter word nets or knowledge graphs. We could also think about computer vision, where we encounter 3D shapes or compositional data in image and video analysis. And then finally, we encounter in many machine learning methods subroutines that are matrix valued, so where we are working with matrices. And in all these cases, there are usually ways of representing the data in a classical Euclidean setting and then performing the downstream analysis in those spaces. But instead, we could also represent the data in a space that is more naturally aligned with its intrinsic geometry and then adapt our algorithms to those geometric settings. And we will see throughout the talk that this can be very beneficial. So in general, when we develop methods for machine learning and optimization, we want methods that are scalable, so that are efficient enough, so that they scale to the kind of large scale problems that we encounter in applications, and that are also come with provable guarantees, so that we understand very well when they work and also why they work. And throughout the talk, I'm going to argue that understanding the geometry of the problem will allow us to phrase it in the right way, which allows us to achieve those two goals. So the talk will have two parts, which cover different lines of my work in this area. The first part of the talk will be about machine learning and hyperbolic spaces. Here we're gonna talk about why hyperbolic spaces are particularly suitable for representing hierarchical data. So in particular, we will see that in hyperbolic spaces, we can represent hierarchical data with high accuracy and low dimensions, and that will allow us to gain performance gains if we perform a machine learning task directly in hyperbolic space as opposed to in Euclidean space using more classical Euclidean methods. And then in the second part of the talk, I'm going to talk about Riemannian optimization. So this line of work is motivated by metrics valued machine learning problems, where I'm particularly interested in problems that are non-convex when we phrase them in a Euclidean setting, but that fulfill a weaker notion of convexity that corresponds to convexity in a Riemannian setting. So by translating the problem onto a suitable manifold, we can use tools from convex optimization to get global convergence guarantees, which can be really helpful and really speed up our algorithms. So for the first part of the talk, let me start a little bit more general than hyperbolic spaces, namely with geometric representation learning. So starting from a data space where our data set could be one of those examples that we've seen on the first slide, our first task is to identify a good representation space, which can be a Euclidean space, but can also be a manifold. And once we identify a good space that aligns well with the geometry of our data, we have to find a way of computing and embedding. So of computing representations of our data in those continuous spaces and doing that in a scalable and efficient way. And then once we have those representations, we want to utilize them for downstream analysis, for downstream machine learning tasks. And many of the algorithms that we have available for doing that assume a Euclidean setting. So when we deem manifold to be more suitable than Euclidean space, we have to generalize and translate those algorithms into continuous spaces, into continuous manifolds, sorry, which then allow us to utilize those representations in the downstream analysis. So first, for learning good representations, what is a good embedding? A good embedding is a representation that preserves the similarity relations in our data space. So for entities or data points that are close by in the data space, we want them to also be close by in the target space, and the similar entities should be far apart in the target space. And for efficiency, we usually aim to have a low dimensional representation, because many of the algorithms and methods that we will use in downstream tasks have a complexity that scales in the dimension of our space. So it's good to aim for a low dimensional representation, because this will give us more efficient methods. So we've already seen that the task of learning representations has two parts. So first we have to identify a good embedding space, and then we have to find a fast and scalable way of actually computing the embedding. And for identifying the embedding spaces, the key is to find a space whose geometry aligns well with the geometry of our data. And why that is so important, I want to illustrate on the example of the Mercado projection. This goes back to the Flemish geographer Mercator, and it's a way to map from the surface of the Earth to the world map as we know it. So our data space here is a spherical geometry, assuming that the Earth is approximately a sphere. And then our target space here is the two-dimensional Euclidean plane. So now what happens with this projection is shown here. So we start with the usual world map as we know it, and then we rescale to the actual sizes of the land masses. So as you see, close to the equator, the distances are pretty well preserved. But as we get further away from the equator, the sizes of the land masses changes dramatically. So to give one concrete example, Mexico, which lies directly at the equator, and Greenland, which lies far away from the equator, appear in the usual world map to be very different in size. So Greenland appears to be much, much larger, but if we compare the actual size of the land masses, they're about comparable. And this representation error is what we call distortion. And this can be very harmful in downstream analysis, because as you can imagine, if we try to learn a model on such data with a representation error, then this error will proceed into our model and will make our model more inaccurate and error prone. And this representation error here is a consequence of the fact that there's no way to faithfully represent spherical geometry in a two-dimensional Euclidean space. So here the representation space is not well aligned with the geometry of our data, and this leads to these quite dramatic errors in the representation of the size of the land masses. So one of my recent papers has looked at identifying good representation spaces. So understanding the geometry of our data and connecting that to the geometry of potential embedding spaces and finding a good alignment there. So focusing on relational data, so we have a data set where we have access to a similarity measure, so we can measure similarities between data points. Such data structures we can, for instance, represent in a graph. And then potential spaces that one could consider for embedding that have certain nice mathematical properties and are well understood are, besides Euclidean spaces, hyperbolic and spherical spaces. Hyperbolic spaces have a negative curvature, and spherical spaces have a positive curvature. So just high dimensional equivalence of the sphere as we know it. So in order to find for a given relational data set what is a good space for representation, we have to find a good approximation of the curvature in our data, which will then tell us which space to consider. And if we look into the mathematical literature, for certain homogeneous types of graphs, this is actually well understood. So for instance, we know that lattices embed very well into Euclidean spaces, and we know that trees embed very well into hyperbolic spaces. But the data sets that we encounter in practice look more like this. So we'll have
Is it okay if I cut in with questions, or do you prefer me to wait till the end?
Maybe I stop between the two parts of the talk and then,
okay. Cool.
Okay. Yeah, so the data that we encounter in practice is looks more like this, just much more complex. So this is the well-known karate club example, where you have certain substructures that are cycles, for instance. So more a feature that we find in spherical geometries. So an indicator of positive curvature, or substructures that look more like a tree. So we have these heterogeneous data structures, and we can't directly apply those classical results from the mathematical literature. Nevertheless, we can take some guidance from them. So the measuring curvature in these data sets is closely related to measuring volume growth. So in fact, the reason why lattices embed well into Euclidean space is because they have a polynomial volume growth, and we also have a polynomial volume growth in Euclidean spaces. And in trees, we have an exponential volume growth, just as we have in hyperbolic spaces. That's why the geometry aligns well there. So for these heterogeneous data structures, in order to get these kind of estimators as well, we can, without going into too much details, there are ways of approximating the curvature of such graph structures and using that as a proxy for an embedding space. So in my paper, I'm proposing a scalable way, so a combinatorial heuristic that we can efficiently compute even for large scale graphs, which allows us to approximate the embedding curvature and then choose a suitable embedding space. And this also comes with some provable guarantees. In particular, it connects to a large body of work in discrete geometry on graph curvatures. So for instance, well known here is chromostatic hyperbolicity, which tells us something about tree-likeness and embeddability into hyperbolic spaces, or discrete notions of Ricci curvature that myself and collaborators and also many other people have studied. So with that quick excursion into more general embedding problems, let's focus on hyperbolic spaces. So as we've already briefly seen, hyperbolic spaces are very good for representing trees, because here the geometry aligns well with that of hyperbolic spaces. And examples where we encounter that in practice are, for instance, compositional data in computer vision, word nets and knowledge graphs when we study languages, or social networks, for instance. So just to reiterate that point with the volume growth, so if we look at a tree here, schematically shown as a binary tree, and we go down the levels of the tree, then the number of vertices grows as 2 to the k, right? So this indicates that we have an exponential volume growth. And in a hyperbolic space, the exponential volume growth is easy to see in this nice artwork from MC Escher, which represents one specific model of hyperbolic space, namely the Poincare ball model, which constructs a hyperbolic space in the Euclidean unit ball. And here the exponential volume growth can be seen as follows. So each of those beds in the pattern have the same area when measured with respect to the hyperbolic metric. So close to the center of the Poincare plane, with a small radius, we can place 3 such beds. And then as we increase the radius and we go further towards the boundary, the number of beds with the same area that we can place grows very fast, in fact, grows exponentially, right? So that's a nice way to see this exponential volume growth in hyperbolic spaces. And we want to make use of that effect for representing these exponentially growing structures. So here is one example for embedding a word net into hyperbolic spaces. This is using Poincare embeddings, which was one of the first scalable methods for embedding data into hyperbolic spaces by Nickel and Keeler of Facebook Research. And here we see a word net with words related to mammal. So mammal as the most general concept, or the root of the tree, is placed very close to the center of the plane. And then as we go down the levels of the tree, we encounter like rodent or carnivore, canine, here, more general concepts. And then as we get closer to the boundary, the tree spreads out more, and we get to more specialized concepts, like down here, If we follow the branch with canine, we see beagle and German Shepherd, for instance, as specific types of dogs, and further down with respect to the levels of the tree. So this whole area of machine learning and hyperbolic spaces has in particular focused in two different directions. So the first one that we just talked about is aspects related to representation learning. So identifying for a given data set what is the right embedding space, whether it's hyperbolic space or spherical space or a mixture of spaces, like mixed curvature embedding spaces, for instance. And then also finding scalable and efficient ways of computing such embeddings that are efficient enough that we can also use them for the kind of large scale data that we encounter in practice. And the second line of work has focused on actually utilizing those representations in downstream machine learning tasks. Here, much of the work has focused on empirical methods. So people have proposed hyperbolic equivalents of support vector machines and neural networks, for instance. And on benchmark data, those have been shown to have a very good performance, also in comparison with the Euclidean counterparts of those methods. But what has been missing from the literature was really a theoretical understanding of that problem. So first, providing complexity guarantees of how well we can expect those methods to perform, as we have for Euclidean counterparts of support vector machines, for instance. And then also really understanding the trade-off between hyperbolic and Euclidean methods from a theoretical perspective and providing guarantees on that. And my collaborators at Google and myself have looked at that for the large margin learning problem in hyperbolic space. And this is what I want to focus on for the rest of this part of the talk. So just to repeat the problem that we're looking at. So we want to learn a large margin classifier, meaning a separating hyperplane, where we just consider a binary classification task, but you could extrapolate from that work to a multi-class classification problem. And in the Euclidean setting, the traditional approach here is the Perceptron algorithm that's been known since the 1950s. So I'm sure everyone in the audience is familiar with that algorithm, but just for completeness, it's illustrated here. So our first task for looking at that problem in hyperbolic space was to translate or generalize the perceptron algorithm to hyperbolic spaces. So in hyperbolic spaces, what we learn is schematically shown here on the right. So we have in gray the hyperbolic manifold. So this is a slightly different model than what we've seen earlier with the Poincare ball. In hyperbolic spaces, we have many different models and geometric ways of formalizing hyperbolic space, and each of them highlights a different geometric aspect. So depending on which geometric aspect we want to utilize, certain models are easier to use, but each of them are isometric in the sense that we can map in between them and preserve all distances. So everything I'm going to say here would also apply to the other models of hyperbolic spaces as well. So, but utilizing this, which is called the Lorentz model of hyperbolic space, we have in gray here our hyperbolic manifold. And what the perceptron learns is a Euclidean hyperplane, here shown in red. And the intersection between that hyperplane and our hyperbolic manifold is the decision boundary. And our Euclidean hyperplane is parameterized by a vector W. And then in order to classify a point X on the hyperbolic manifold, we take the Minkowski inner product, which takes the place of the Euclidean inner product in hyperbolic spaces. And then based on the sign of the Minkowski product, we classify the point into one of the two classes. So when we want to train that model, the conceptual idea is very similar to what we do in Euclidean spaces. So we have a very similar update rule. And whenever we make an error, we update our classifier. What is different here is that we need this normalization step. So the geometry here is somewhat more complex, and just by performing the standard update rule, we are not guaranteed that our classifier our updated classifier intersects with the manifold. So we might have to map onto a different hyperplane, which has the same classification power, but does intersect intersect the manifold. So we just have to insert this normalization step, and then one can show theoretically that by inserting such a step, our updated classifier will always remain valid. And then we can also look from a theoretical perspective at the complexity of that model, and can show that the perceptron in hyperbolic spaces has a complexity of on the order of 1/signage of gamma. So after that many steps, we achieve a margin of gamma. And this is about comparable to what we have in Euclidean spaces, where the complexity guarantee is on the order of 1/gamma squared. So for small margins, we do slightly better. For larger margins, we are about comparable. So this algorithm only gives us the means to compute a separating hyperplane, but not necessarily the one that achieves the largest margin. So if we want to learn such a more optimal classifier, we have to optimize for the margin. So here we have to consider a geodesic notion of margin, which we can, with a simple geometric argument, derive from the hyperbolic metric. And then we can formulate this large margin classification problem that we want to solve. And for training a support vector machine style algorithm in hyperbolic spaces, we also need a notion of margin losses, which are defined in principle analog to what we consider in Euclidean spaces. That's also why we named them in the same way as we would name them in Euclidean spaces, just defining equivalent functions that have a similar behavior in hyperbolic spaces. So the actual algorithm that we want to train has one additional assumption. We not only want to learn the classifier that achieves the largest possible margin, but we also want to learn a classifier that is robust to adversarial perturbations. This is encoded in our robust loss function here. So we optimize this a loss with this min-max structure. So we have an outer loss, which characterizes the loss, the classification loss over a training set. And then our inner loss characterizes how well our algorithm does with respect to adversarial perturbations, where we define an adversarial example as taking a point in the training set on the hyperbolic manifold and perturbing it up to alpha along the manifold. So in order to train such a classifier, we also have to take an adversarial training approach. So in each iteration of the algorithm, we take a subset of the training data and perturb it on the manifold. So construct the local maximizer with respect to the robust loss. This will get us a set of adversarial examples that we can then add to the training data and enrich the training data. And then we can update our classifier over this enriched training data set. So very briefly, generating adversarial examples in hyperbolic spaces. So in Euclidean spaces, it is usually enough to add a simple perturbation in the L1 or L infinity norm to a point to generate an adversarial example. In hyperbolic spaces, we have the added difficulty that we have to remain on the manifold. So one might think at first that we have to solve a constrained subroutine, so which locally optimizes for the loss, but then also has this constraint that we remain within a hyperbolic distance alpha along the manifold of our point. We show in our paper that this can be reduced to a Euclidean linear program, which can be solved in closed form, very fortunately. So this subroutine and this additional constraint that we have to remain on the manifold does actually not introduce any expensive bottlenecks, but can be sufficiently efficient solved so that we still have a very efficient algorithm. And then we have to consider how to actually update our classifier, where we have two variants of the algorithm. One uses a gradient descent update rule, and another one uses an empirical risk minimizer. So for the gradient descent style algorithm, we have a typical gradient descent update rule, similar to what you see when you work in Euclidean spaces. And then we can show a sample complexity for that, which is polynomial. So this results in an efficient algorithm. Since this is one of the central results of this paper, I want to give a few ideas on the proof, but we'll keep it very briefly in the interest of time. So the key step here is to analyze what we call the adversarial perceptron. So a much simplified version of this full gradient descent algorithm, where we essentially take the hyperbolic perceptron and add adversarial perturbation to that, and then analyze both the complexity and also the robust margin that this algorithm achieves. And then building on that auxiliary result and then using standard tools that you would also use when analyzing the standard gradient descent, we can put that together and derive this polynomial time guarantee. Importantly, adding those adversarial examples is critical to achieving such an efficient algorithm. So if we were to take out this adversarial training subroutine and essentially just work with the hyperbolic support vector machines, there are pathological examples that we can construct, which would require exponential time to convergence. So this adversarial augmentation of the training data set is really critical to making this an efficient algorithm. And then moving on to the second variant that we have, which uses an empirical risk minimizer, we can show sample complexity of the following form. Here the proof is very different from the quick sketch that we've just seen. It uses a packing argument, so we construct a spherical code in hyperbolic spaces, which then allows us to find a sample complexity that scales exponentially in the dimension of the embedding space. And interestingly, a similar result has been shown for Euclidean spaces in 2016 by Charles et al. So we're also using a packing argument and essentially a counterpart of this algorithm in Euclidean spaces. They also showed a sample complexity that scales exponentially in the embedding dimension. And this allows us to directly compare for algorithms that are counterparts of each other in hyperbolic and Euclidean space, the sample complexities for a given problem. So in particular, if we go back to our original motivation of representing hierarchical data, which looks like a tree in Euclidean and hyperbolic spaces, and looking a little bit more into the embedding literature, we find that trees embed very well with almost no distortion or representation error in hyperbolic space as low as dimension 2. But in Euclidean spaces, we would need on the order of log of the size of the tree squared to get a decent representation error. And then comparing that with the guarantees that we get, you can see that the hyperbolic guarantees are actually much superior because of the lower embedding dimension that we achieve. And this can also, what I stated here informally, this can be rigorously proved by quantifying the effect that this distortion, this representation error, has on the margin guarantees that we get, and then considering a trade-off between embedding dimension and having a low representation error for the margin guarantees. So much for the theory. I also want to show a few experiments. Here we work with a subset of ImageNet that we have pre-processed so that it's separable. So we consider 2 subtrees after clustering ImageNet, which is basically the pre-processing ensures that all the assumptions that we make in all the theoretical assumptions that we make are fulfilled for that data set. And then we embed it into hyperbolic space and run our adversarial gradient descent on that data. So here we see for 2 different loss functions, the hyperbolically squares loss and the hyperbolic hinge loss, the results. And here we see, just as the theory predicts, a larger adversarial budget allows us to achieve a better margin, but also have a larger training time. And then here we can also compare against the state of the art. So those are, as previously mentioned, an extension of support vector machines into hyperbolic spaces. So in our framework, this corresponds to the algorithm with no adversarial perturbations, and we see that we significantly improve over those with that adversarial augmentation of the data set. And then in the second experiment, we tested out the perceptron approach and basically illustrated this dimension distortion trade-off that we talked about 2 slides ago. So here we took the same data set and embedded it into Euclidean and hyperbolic space of different dimensions, and then tested the Euclidean perceptron against the hyperbolic perceptron and looked at what the minimum dimension is so that we that the algorithm converges so that we achieve a 0 test error. And geometrically, this happens as soon as the data is separable. So now we have pre-selected a data set that is separable. So basically, this shows us the minimum dimension in each space such that we can represent the structure of the data faithfully enough to preserve the separability. And we see that in hyperbolic spaces, we achieve that in as low a dimension as 8. But in Euclidean spaces, we have to go to a much higher dimension. So even in 16 dimensions here, we still make a very significant error because we cannot faithfully represent the geometry of the data and preserve the separability. Okay, and with that, the first part of my talk is done. So if there are any questions on the first part, that would be a good time to ask.
I also wanted to say people can add questions in the Q&A or they can ask in chat. So while people simmer and type. Okay, so there's it seems to me like you've kind of given us 3 reasons why we would want to represent our data in hyperbolic space, for example. The first reason is because it more naturally fits the original structure of the data. So there's sort of we're representing the meaning of the original data anyway. Mm-hmm. The second reason, and I'm looking for pushback if I'm wrong. The second reason is your bounds on sort of performance are actually improved by doing this. So for instance, those theoretical convergence arguments about how big the margin is and also how robust they are to adversaries is actually improved. Mm-hmm. Which is probably tied up in the previous thing, but this is the mathematical version of the previous thing. Mm-hmm. And then the third reason that I'm getting a feeling for is also separability seems easier to achieve, and that feels very tied up in the second thing, but maybe they're actually distinct points. Is that a reasonable summary? Yeah, that's a very good summary. So actually all 3 points are very closely connected. So okay. the overarching reason behind, so the first one is more the actual reason, and moral. And the second 2 are more like the consequences of that. But yeah, as you said, so by aligning the geometry of our space in which we are working very well with the data, we can very faithfully represent features of the data, such as separability, in a very low dimensional space. And this then significantly speeds up our algorithms, which we observed both in the validation experiments, but can also theoretically quantify. But that all is connected to having the geometry of our data well aligned with the geometry of the space in which we are working in. Okay, awesome. And then my second question is more on the sort of details of I just don't understand the data set perfectly. So you're looking at ImageNet plus hierarchical labels from WordNet. So is that roughly saying we have a label about the whole image, then we have a label of some of the things in the image, then we have a label about some of the things in some of the things? Is that what it is? No, so it's more yeah. So we have to labels. It's actually just a way of. So this is just a validation example. This is just a way of getting a data set that fulfills our theoretical requirements. So in order to, since we make an assumption that the data is separable, we have to ensure that the data on which we are testing that is also separable. So we can cluster ImageNet. So for instance, we could take. I don't actually remember which subtree we used, but we could go back to this mammals example that we had in the beginning. So we could look at images of mammals, and then maybe we select the canine subtree with images of dogs, and then the one with cats with images of cats. And then we should be able to, if we can faithfully represent the structure in our data, to have the dogs separated from the cats, and then learn a separator. Okay. Okay.
Yeah, so just a pre-processing to ensure that we have our separability, and that there's a realistic chance of, if we faithfully can represent the data, that we can learn a separator and that our algorithm converges.
Yeah, because I can think of data sets where I have hierarchical relationships, but I'm trying to think, do they fit into this structure or not? And yeah, okay. And then also there's some questions in the Q&A if you want to take a look at those.
So one question by Jonathan asked about, so if we try to find a good embedding curvature, then yeah, we're starting with relational data in the sense that we can measure similarities. So you could certainly think of that as an adjacency graph with numerical data. So I guess if you have a table of numerical data, that's maybe not relational data. So that maybe doesn't really have the form that we are assuming here. So we are assuming we have some collection of data points, and you have relations in your data points that you. So it doesn't have to be numerical. It could be images, and then you can measure the similarity between images. Or yeah, you're starting with a relational data set, for instance, like social networks. Maybe you have like a friendship graph or something, right? Then there are similarities encoded in this data structure. So I hope that answers the question. So yeah, if you have a table of numerical data, and it's there, relations in the data set are not what you want to analyze or what you want to work with, then those methods are probably not the best ones to use. And then the second question, my understanding is that neural networks do a good job of getting embeddings. Do these achieve the appropriate choice of geometry automatically, or does introducing an explicit geometry embedding learning step before neural network training give an additional performance gain? Yeah, so these geometric embeddings, that's certainly more like a pre-processing step. But then there are at least empirical methods that work with, that take as an input non-Euclidean data. So one of the methods I briefly mentioned earlier is hyperbolic neural networks, which works with hyperbolic data. So data that is represented in hyperbolic space, and then uses that as an input. I'm not aware of any like direct end-to-end methods that sort of start with a relational data set, for instance, and then directly find the best embedding. I think it's more, at least from what is right now in the literature, it's more as a pre-processing step. Okay, so Jonathan, I hope I answered your questions. I'm moving on to another one. Why do you use adversarial robustness as opposed to other types of regularization? Yeah, that's a good question. You could certainly also look into other types of regularization. That's the setting we analyzed. But I think there's certainly more work to do in that area and other types of regularization that one could consider. One motivation for using that specific one was also this other Euclidean algorithm that I mentioned, where we essentially had the same setting that we considered with the empirical risk minimization, which had been considered in Euclidean spaces. And since we had those sort of parallel results in Euclidean spaces, this really allowed us to quantify a trade-off between the two methods, which was one of the goals of that project. So that's also another reasoning why we chose that particular type of augmentation. How does one consider graphical data sets which contain local subsets that are quite tree-like and distinct subsets which are quite cycle-like? I'm not sure in which direction that question goes. So for embeddings, so how many embedding methods for non-Euclidean spaces are essentially variants of multidimensional scaling. So you would start with the distances in your data space. So if you have a graphical data set, you have maybe path distances in graphs, And then you have your target embedding space where you initialize each node in your graph to some point. And then your objective function basically quantifies the error between the distances in your data space and the distances in your target space, and then tries to minimize that error. So you want to represent the distances in your original space as faithfully as possible. So those embedding methods don't really make any assumptions about the structure of your data. They, work with everything, but the objective function that you quantify, of course, depends on the geometry of your target space. And then if you align your target space better with the geometry of your data, then you can achieve a lower error. So by doing this pre-processing step, by analyzing the structure of your data, trying to understand whether it's more tree-like or more cyclic, so cycle-like, how you called it, helps you to find out what is the best how to set up my multidimensional scaling. What's the objective function with respect to what metric do I measure error? Do I measure distances in my target space? So to kind of give you the right setup that achieves the lowest possible error. So this is why those pre-processing methods, but they would come before you actually compute the embeddings. Yeah, so I hope that answered the question. And then can you explain at a high level how data and hyperbolic space are related? Perhaps you can share examples between written words and hyperbolic spaces. Yeah, so in those word nets that we've seen, we have a hierarchical structure. So this is really what you make use of here, the hierarchical structure in your data. So basically any data set that you could consider that has hierarchies, if you would encode that in a data structure, you could use a tree. And then I tried to motivate earlier, at least with pictures, this connection between hierarchical data, between trees and hyperbolic spaces, where in hyperbolic spaces you look at volume growth, and in these discrete structures like trees, volume growth basically corresponds to growth in neighborhoods. So if you go down the levels of the tree, you could consider that as looking at larger and larger neighborhoods of your root node. And then if you have truly hierarchical data, this also grows exponentially. Whereas if you would work in a lattice and you pick one specific node, and then you look at the neighborhoods of that node, that only grows polynomial in size. So such a data structure would not embed very well into hyperbolic space. And then if you wanted to use representations of perform some downstream analysis on such a data structure, then probably those hyperbolic methods would be much less efficient than using the Euclidean methods. So in such cases, you should certainly use the Euclidean methods because there the geometry is better aligned. Okay, I hope that answers the question. Okay, so if I haven't answered your question, then maybe just write it in the chat again, and then at the end, we can go back to questions on part one. But let me start with part two maybe now. Okay, so as I said, the second part is motivated by a different set of machine learning problems that we encounter, which are metrics valued. So here you can think of machine learning tasks that have a subroutine where you optimize over a certain class of matrices. So maybe over orthogonal matrices or fixed rank matrices or positive definite matrices. And instead of using Euclidean optimization methods to optimize over such classes of matrices, you could also translate the problem onto a Riemannian manifold, because each of those constraints that form these classes of matrices has a corresponding manifold structure. Like for instance, for orthogonal matrices, we have the Stiefel manifold, or fixed rank, the Grassmann manifold, and then very popular for positive definite constraints, we have the PSD manifold. So some concrete applications or subroutines that you could think of are, for instance, averaging problems. So if you have a machine learning task where you want to average Gaussians, then the covariances of your Gaussians are positive definite matrices. So instead of working in your Euclidean metric space, you could work on the PSD manifold. Or if you have noisy measurements that are encoded in data matrices, and you want to synchronize them to denoise them, what you're computing is a rotation matrix, and therefore the problem can also be considered on the manifold corresponding to the special orthogonal group. Or for instance, if you have a matrix completion task, you have a fixed rank constraint, so you could translate the problem onto the Stiefel manifold. One specific algorithmic benefit that you can get from this change in geometric lengths is geodesic convexity. So as we know, when we perform optimization, it's always highly desirable to have convexity because that guarantees that a local optimum is also the global optimum. So basically from any feasible initialization, our algorithm will converge to the global optimum. Now, of course, many machine learning problems are non-convex, and also some of these subroutines that we've just seen are non-convex, but some of these matrix valued problems fulfill weaker notions of convexity, which we call geodesic complexity, and which corresponds to a more general notion of convexity on Riemannian manifolds. So due to that property, we can use tools from convex optimization in Riemannian spaces to achieve these nice global convergence guarantees. So basically, by switching the geometric lengths, we have translated our problem from a non-convex problem to a convex problem in a different geometric space. So some examples in that class of problems are, for instance, these averaging problems, which are special instances of the Kauscher mean problem, or computing Prask-Kampf-Lieb constants, which relates to the operator scaling problem, which is connected to many problems in statistics and theoretical computer science, generalized eigenvalues, and so forth. It's a large class of problems where you have this nice property. So this has driven a lot of research in Riemannian optimization and translating optimization tasks from Euclidean spaces to Riemannian spaces. Much of this work has focused on unconstrained optimization, but oftentimes we have tasks where we have additional constraints. So maybe we have a problem that has an interval constraint or a determinant constraint. And in such cases, we need tools for constraint optimization. And that has been studied very little before my work with Sophie Tra, who's a professor at MIT. And I'm going to spend the remainder of this part of the talk to talk about this work on constraint optimization. So the setting that we're considering here is a smooth function defined on the Riemannian manifold that we want to minimize. And we require the minimum to lie in a compact geodesically convex region on the manifold, which is defined by this constraint set script X. And if we take inspiration from the Euclidean setting, how constraint optimization tasks are approached there, then there are essentially two classes of algorithms that we could consider: projected gradient methods and projection-free methods. So following with the Riemannian optimization literature, which has mostly focused on unconstrained settings, and just as in the Euclidean setting for unconstrained optimization, gradient descent and its variants are probably the best approach that you could use in many settings. And so the natural approach for going from the unconstrained to the constrained setting in Riemannian spaces would also consider extensions of Riemannian gradient descent. And then this other class of algorithms, Frank-Wolfe methods, have not been considered in a Riemannian setting, but they can have benefits, as I will explain shortly. And this is why we focused on extending those Frank-Wolfe methods as well to the Riemannian space. So for projected gradient methods, what the idea is that starting at a point xk, we evaluate the gradient information to find a feasible descent direction, and perform with that information a standard gradient descent update. But here we have no way of incorporating the constraints explicitly. So what happened is that we might step out of the feasible region where the constraints are fulfilled, which is here shown in blue. And in such cases, we have to project back onto the feasible region. So we have to compute a projection. And depending on the geometry of our constraint set, this can be quite expensive, especially when working in Riemannian spaces. So what we could consider instead, projection-free methods takes the following approach. So starting at a point xk, we also evaluate gradient information to find a feasible descent direction. And then we call a subroutine, which is called the linear oracle. And this finds an extremal point along the feasible descent direction, which still fulfills the constraints. So an extremal point in the feasible descent direction at which our constraints are fulfilled. So here in our sketch, this is a point, the linear oracle returns a point zk, which lies on the boundary of our feasible region in the feasible descent direction. And then we linearly interpolate between xk and zk and step along that line with a certain step size sk. And since we assume our constraints to be convex, any point along that line will be in the feasible region, and we don't need to compute any projections back. So in practice, we have to compare the cost of computing a projection with the cost of solving this subroutine, this linear oracle. So now to translate that algorithm or generalize that algorithm to Riemannian spaces, we have to look at the two core components of that algorithm, the subroutine, the linear oracle, and also this interpolation step that computes the update. So in Riemannian spaces, we evaluate the Riemannian gradient instead of the Euclidean gradient to find a feasible descent direction. And then instead of performing these linear interpolations, we look at geodesics. So when we are on a manifold, the shortest path along the manifold between 2 points is what we consider a geodesic. And the length of that will also be the geodesic distance, so the distance on the manifold between those 2 points. So basically, instead of looking at lines that we have in a flat Euclidean space, we look at a curved path along the manifold as the closest connection between those 2 points. So for getting that interpolation step here, we consider geodesics with a start point at xk and an endpoint zk, which is that extremal point that we get from the linear oracle. And then we step along that geodesic with our step size sk. So usually something like 1/k, which decreases with the number of iterations. So just as in the Euclidean setting, the key step in that algorithm is not really computing that geodesic, because if we work on a specific manifold, we usually have a good way of constructing geodesics, but it can be challenging to solve the subroutine, this linear oracle. In Euclidean spaces, this is a convex problem, so usually relatively easy to solve. Unfortunately, when we generalize to the Riemannian setting, this is in general a non-convex problem. So we can't really expect to have a good solution for any manifold that we're considering. So a sort of standard tool that we could use in any case that we encounter and always get an efficient solution. But we will see later on in the talk that if we specialize to a certain manifold, there we can find efficient ways of solving that linear oracle. Before specializing, I want to comment on the convergence of that algorithm. So we can show a sublinear convergence rate. So after k iterations, we are on the order of 1/k close to the optimum. For both non-convex and convex objectives, where of course only in the convex case, this is a global guarantee. In the non-convex case, this is only convergence to some local optimum. And if we make some stronger assumptions, there are variants of the algorithm that you could consider which have a linear convergence, so which are very fast, but only under these stronger assumptions on the location of the optimum and also the convexity of our objective. And the really critical point here to put this result into perspective is to compare with the Euclidean Frank-Wolfe method. So if we were to perform the optimization task in Euclidean space, and also these Riemannian gradient methods. And both of them also have a sublinear convergence rate. So just by looking at the number of iterations, we can't really decide between the two algorithms. And we really have to compare the cost of computing the projection with the cost of solving the linear oracle to find the best method to use. I think I'm pretty short on time, so I'm gonna try to go through it a little more quickly. Just to mention, this setting that we're considering so far considers deterministic objective functions, which is not typically what we encounter in machine learning. So it's important to think about extensions to this work into stochastic settings. So maybe to the minimization of black box functions or to empirical risk minimization. Which we have done in a follow-up paper. And to make it very brief, those methods extend to stochastic settings, and we can also recover the theoretical guarantees in those stochastic settings. Okay, and now to give one specific example for how to efficiently implement that method and use in practice, let's focus on the PSD manifold, so the manifold of positive definite matrices. And let's consider constraints that are in interval constraints. So we have in Löwner order a lower and an upper bound. And problems of that form are averaging problems like the Cauchy mean problem, for instance, or computing Wasserstein barycenters. And in this specific case, we can solve the Riemannian linear oracle, so this crucial subroutine, very efficiently. In fact, we can even solve it in closed form. So I'm not going to go into details. I'm just going to show the theorem. So here we have a closed form solution, which can be very efficiently implemented and computed. So this does not introduce any bottleneck and is very scalable in practice. And to illustrate that, I want to just very briefly show some numerical examples. So these are for the Cauchy mean problem, for averaging Gaussians. And here we see in blue the deterministic Frank-Wolfe method, and in dotted lines, those stochastic variants that I briefly mentioned. So here we see a significant speed up compared to the deterministic methods because we work with gradient estimates, which are faster to compute than full gradients. And then here we compare against some deterministic methods and also some stochastic methods in the literature, and we see that we get pretty significant performance boosts by using those Frank-Wolfe methods as opposed to projected gradient methods. Okay, and with that, I'm done. We talked about the fact that in many applications we encounter non-Euclidean data, such as matrices or graphs or trees. And it can be very beneficial to represent that data in a space that aligns more natural with the geometry of the data, and then also perform downstream analysis in such spaces. And we've seen, especially in the second part, that exploiting Riemannian geometry can deliver algorithms which are provably and also empirically superior to standard Euclidean approaches. Okay, thank you.
Awesome. Thank you. That was super awesome. A couple like high-level questions in the second part. So the first question I had is geodesic convexity what I expect it to be, which is simply like it's, you know, every 2 points are connected by a geodesic lie within the domain? Mm-hmm. Okay, great.
Yeah.
Cool.
I should have said that, but yeah, it's exactly what you would expect.
Okay, cool. I just want to make sure that I didn't guess poorly. All right. And then my second question is, I feel like I was a little bit confused, like how you know that you should be working in one of these like Riemann geometries to be solving your problem in the second case. And you talked a little bit about the type of matrices that you're going to be working with, and the type of matrices that you're working with is kind of determining what manifold you're on, and that gives you the sense. But like, I don't know, is there like an easy way to kind of like take away of like when I should be thinking about this sort of thing?
Yeah, so that's a good question. I don't really have like a sort of systematic answer to that. Okay. But those Riemannian representations also, so in theory for the problems where you can show that they are Euclidean non-convex but geodesically convex, you should certainly work in Riemannian spaces because you know it just gives you better guarantees, and you always want to perform convex optimization whenever you can. But from a more practical perspective, there are certain matrix manifolds that we understand better, and where it is easier to, for instance, implement a geodesic or compute a gradient or things like that. And then there are also certainly manifolds where that is harder to do. So I would say if you have these spaces like the PSD manifold, for instance, where those are very well understood and there exist nice packages for computing that in practice, it's certainly worth looking into using Riemannian methods because all the tools are there. And we know from many problems that there are also theoretical benefits that should translate into practical gains. But yeah, I don't think there's a sort of systematic way like to say, okay, in this problem, I should definitely use Euclidean methods apart from things like geodesic complexity.
I see. Okay. Okay, so we're out of time, and a lot of people had to jump off because they have other meetings. So we'll call it there. I have a few questions that I'll hold for after the the thank you. Yeah, thanks to you. And if anyone has any other questions, her contact information should be on the site. I think we linked to her page, but I'll ensure that. Cool. Thank you so much. This was great.
Thank you for the invitation.
And then my other two questions.
Go ahead.
Okay. So the first one is, and I think one of the questions in the Q&A was maybe like sort of getting at this, but not quite, which is we have these like graph neural nets, and graph neural nets are inherently saying like, we're going to build an embedding from the like hierarchical relationship between the data, and we're going to do it sort of implicitly. We're going to do it via these graph kernels.
Mm-hmm.
Now, that doesn't leverage anything about sort of like being very smart about the space that embedding is happening, and so the optimization can happen. So I see that we're losing that part of the like gains. But do you have any sort of like insight as to kind of like the relationship between what these graph kernels are doing for the embedding and what your like, embedding procedure does?
Yeah,
I saved it for after.
Yeah, that's a tough question. So I must say I'm not an expert in graph neural networks, so I only have like recreational knowledge on that. So I can't comment too much on that.
No problem.
I would say at least to my knowledge. So for graph neural networks, those trade-offs, for instance, that I briefly mentioned that we can get for this large margin learning and hyperbolic spaces, for instance, such kind of theoretical results are not known for many problems in hyperbolic spaces, and I'm also not aware of any like theoretical guarantees for graph neural networks. But this is not to say that they couldn't exist. Maybe they are just not known yet. So I think there's certainly a lot of theoretical questions that are still open on understanding rigorously from a theoretical perspective the trade-offs between those methods. And then what I could also imagine that, so for instance, for these very heterogeneous data sets, which don't embed particularly well into hyperbolic or spherical space, but which have a very mixed curvature, like so for instance, for biological networks and biological data, it is known that they are not very hyperbolical, don't have very good hyperbolicity. So for such data sets, these like approaches that are a little bit more agnostic to the geometry and just implicitly approximated are probably more helpful because you don't have to make these strong assumptions. But for data that is very hierarchical, like knowledge graphs, for instance, I would expect that such hyperbolic methods which encode geometry a little bit more explicit should give benefits. At least in theory, we expect that. And I think if we bring the implementation and the practical methods up to speed with what we have in other spaces, then I would hope that we also see this in practice. I think it's just that for hyperbolic machine learning, for instance, there are not too many dedicated software packages and things that are really carefully implemented and can be used in practice. But I think if we catch up there, then we might also see that in practice and maybe comparable performance to graph neural networks.
Yeah, I did wonder, like, what's the package software like situation currently for this? Can I import this in PyTorch and check it?
Uh, no, so for hyperbolic machine learning, I would say that everyone who does who translates an algorithm into hyperbolic spaces has their own implementation and puts it on GitHub. So I don't think there's any sort of curated package. These embedding methods, like the Poincare embeddings from Facebook research, for instance, those are a little bit better curated. They have like also GitHub repositories, but there people have really spent some time in cleaning up those methods and documenting it well. So I would say that's at a point where it's pretty usable and can probably plugged into more applied pipelines.
Okay.
But yeah, for the machine learning tools, this is also all very recent work.
Yeah,
So
I saw
people have just 1 or 2 years ago started doing this. So
Yeah,
it's lagging behind development in other fields.
cool. I see there's another question in the Q&A.
In the takeaway slide, can you provide some data examples for data in its natural space? So with natural space, I just mean that the intrinsic geometry of the data aligns well with the geometry of our space. So for instance, if we have hierarchical data, like either a perfect tree or something like a knowledge graph, which is very close to a tree, then the intrinsic geometry of that is negatively curved. So a natural space for that would be a negatively curved manifold. Or if we, very trivial, but if we have this example that we saw at the very beginning, where we try to map the surface of the Earth onto a world map, the geometry in our data space lies on a sphere, right? We have geographic distances between cities, for instance, or scales of land masses, which have are measured with respect to a spherical metric. So in that case, the intrinsic geometry in our data space is spherical, and then a natural space would be to represent that also on a sphere and not in this two-dimensional word map, which introduced all these scaling errors that we've seen. Yeah, so those are maybe just some examples.
Awesome. Thank you so much. This was super cool. Yeah, thanks again.